Hello and welcome to the YouTube channel of Canara Engineering College. In this video session, we'll start with the module 4 of microcontroller and embedded system. In module 4, there are basically 4 chapters to be studied where we'll be looking into the various characteristics, various ways in which the embedded system is being built, developed and manufactured. As a part of the first chapter, we'll be looking into the characteristics and quality attributes of embedded systems. So the first thing what I need to know here is we are not too confused with the term characteristics and attributes. So characteristics is a different term and attributes is a different term. So here attributes means the properties of an embedded system. So you need to look into the various characteristics or the general characteristics of an embedded systems and the various properties of an embedded system in this particular chapter. So as you all know, embedded systems has been built to operate in a environment or to be in contact with the external world. No matter whatever is an embedded system or whether it's an embedded system, it will always be having a characteristics which will be describing the system. It will have various characteristics depending on the functionalities or depending on the way in which it has been built or depending on the environment in which it is working. So those are all the very specific characteristics. What we are going to learn in this particular chapter is we are going to study the general characteristics which are exhibited by the embedded system. After that, we need to look into the attributes. Attributes means we need to look into the properties of a embedded system. When it comes to the properties of an embedded system, we need to look into the functional and non-functional attributes. The properties what will be exhibited by the embedded system when it is turned on or when it is online, and we also need to look into the attributes of the embedded system when it is being turned off. So we need to basically look into the non-functional aspects that are very important if you need to know the embedded systems. So we have already studied the functional aspects. We need to know the non-functional aspects also. But if you are a designer of an embedded system, you need to know the functional as well as non-functional aspects in detail. So as I said, we will concentrate on the characteristics as well as on the quality attributes of a embedded system. Moving on further, we'll check out what are the basic characteristics or what are the general characteristics of an embedded system. So you can check out here, embedded system possesses certain specific characteristics and these characteristics are unique to each embedded system, which means that if you consider an air conditioner, you can consider this to be an embedded system. If you consider a refrigerator, that will also be an embedded system. If you consider a remote control, that will also be an embedded system. If you consider a music player, that will also be an embedded system. Every embedded system will have its own characteristics and those characteristics are unique to each and every embedded system what I have mentioned here. That is what this particular sentence says. The general characteristics or the general characteristics of all these embedded systems are, the first one is application and domain specific. We'll check out what is this application and domain specific. Reactive and real time, operates in the real harsh environment, distributed, small size and weight, and the power concerns. So basically these are the 6 general characteristics what a person or what a designer or what a manufacturer has to know before he actually designs a embedded systems. So let us look into this one by one. The first one is application and domain specific. So if you have designed an embedded system, this embedded system will have its own application and this embedded system is going to work in its own domain. This embedded system cannot be used for other application or you cannot use this embedded system in a different domain. For example, if you have designed an embedded system for a communication domain, you cannot use this embedded system for a music domain. If you have used an embedded system or designed an embedded system for a electrical domain, you cannot use it for an electronics domain, which means the domain wise the embedded systems will have its own specifications. Very similarly, application also. The embedded system what we have designed for an air conditioner cannot be used for a refrigerator. It is not possible to use an embedded system both as an air conditioner and both as a refrigerator, right? That is what this application and domain specific means. The details with respect to that has been given here. Moving on to the next one, reactive and real time. Let us consider a embedded system in which it is like the user will be, or user is going to give a defined inputs and through the input ports, and the embedded system is going to give you the defined outputs, which means that you can predict this is when the embedded system is going to give the output. That is what is real time embedded system means. When it I mean reactive time embedded system means, when it comes to real time embedded systems, the inputs and the outputs of this embedded systems cannot be determined, or you cannot predict it. You cannot say when there will be an input that is coming to this embedded system and when there is an output that will be produced by this embedded system. So here, if you check out, any changes happening in the real world are captured by the sensors and the input devices in real time, and the control algorithm running inside unit reacts in the desired manner to bring the controlled output to the desired level. So here, this is unpredicted one. You cannot say that when your sensors are going to give the input and when it has to produce the output. Whereas in case of your reactive time, you can say, okay, this is when the input is being given by the sensor and this is when it is going to produce the output. So that is what is your reactive and real-time embedded systems are. Real-time embedded systems are used in critical applications, and the reactive time embedded systems are used in non-critical applications. See, it's given here. Real-time system means the timing behavior of the system should be deterministic, meaning the system should respond to the request or task in a known amount of time. Within that given time, your real-time system should give the output. For example, if you speak about a airbag in your automobile, so as soon as there is an accident, your airbag should open up, right? So which means that in a known amount of time, it should give the output. Whereas in case of your reactive time, not necessary. It is not that critical application. Moving on to the next characteristics, operation in the harsh environment. So when you build an embedded system, you need to make sure that the embedded system, whatever you have built, will be operating in all the possible environments in which it is intended to operate. It may be a temperature, it may be a severe shocks, or it may be a high voltages or high currents or any of the conditions. So that is what this particular topic means. For example, if you take a thermometer which is used to measure a human body and a thermometer which is used to measure the temperature of the furnace, normally the way in which it has been built will be entirely different, right? Because you cannot use a thermometer which is used to measure the temperature of a human body to measure the temperature of a furnace. So both are having different applications. It is having its own application. So you need to make sure the embedded system what you are going to build will be operating in all the possible environments in which it is intended to operate. Moving on to the next condition, distributed. Distributed means when you speak about an embedded system, not all the embedded systems are packed inside a single package. It will have different components. It may be having sensors somewhere out, it may be having actuators somewhere out, it may be having displays somewhere out. So whatever peripherals that are present in the embedded system, which are distributed in the various parts of the environment, you can call that particular embedded system as a distributed one. For example, if you take a vending machine or ATM, there is a card reader in a separate section, there is a place in which you will be entering the password, there is a different place in which you will be receiving the cash. It is not all happening in a single place, right? So all the peripherals are connected together in order to form an embedded systems, and all these peripherals are distributed, and when they are connected together they form an embedded systems. Normally distributed embedded systems gives the user the ease to access that particular embedded system. You cannot say that, or you cannot say that I need to have all the components in a single place or in a single package. It can be distributed anywhere. Normally most of the embedded systems will be distributed ones. See, they have given you the example of ATM. They have given you the example of SCADA. SCADA is nothing but distance data acquisition. For example, let me say that you are sitting in one place and you want the data of some other place, maybe the weather report or maybe some other data of other place. You can take the data or you can acquire the data. That particular system is called as SCADA. Or maybe when I say that you sit in a control room and there's a satellite which is moving to moving in a other planet, or maybe it is moving in the sky or in the space. You need to control it. So all that happens via the SCADA or distance data acquisition. That is what is called as distributed embedded systems. Small, weight and size. This one I need not explain to you at all. Normally I expect my embedded system to be as small as possible so that I can carry it, and also I want the weight of that embedded system to be as small as possible. That is what is one of the very important characteristics of an embedded system. In fact, this adds to the beauty of your embedded system. You cannot say that I want my embedded system to be a bigger one. You cannot carry it. You want it to be as small as possible, and the weight of that also should be small. Moving to the next characteristics, which is regarding power concern. So normally when you say there is an embedded system, it means power supply. So your embedded system should be consuming minimum amount of power, so that the power supply whatever you have connected to the embedded system will also be of the smaller size. Not only that, if your embedded system is consuming more power, then the heat sinks what are used in the embedded system in order to absorb that heat that is generated due to the process should also be bigger, right? And these heat sinks are in fact heavier. So you normally design, or when you are designing or when you are buying an embedded system, please make sure that your embedded system is consuming less power. You normally go to buy the what you can call refrigerators or AC. You see there 5-star rating, 3-star rating, 2-star rating. It is all about the power concern. So you normally expect your embedded system to be consuming as less power as possible, so that you can reduce the weight and you can reduce the size and you can also reduce the power consumption. So these are the 6 important characteristics what ideal embedded system should be having. Moving on to the next section of our discussion, we'll be discussing regarding the attributes. Attributes means properties of an embedded systems. So when I speak about the quality attributes, these quality attributes are nothing but the non-functional requirements. Non-functional requirements that are very importantly need to be known by the manufacturer or need to be known by the designer. So what are these quality attributes going to do? Quality attributes are going to have a positive impact on the system development process and also on the end product. The various quality attributes that need to be known are classified into 2 categories. One is called as operational quality attributes. These are called as online properties, and these are called as offline properties. Online properties means the properties of an embedded system when the system is turned on, and this non-operational quality attributes are the properties of an embedded system when the embedded system is off. They are the general properties. So let's check these properties one by one. When coming to the quality attributes or the operational quality attributes, uh, they are response, throughput, reliability, maintainability, security and safety. All are the known terms to you people. Coming to the non-operational quality attributes, they are testability and debugability, evolvability, portability, time to prototype and market, per unit and total cost. Maybe these are the things, maybe these are the 4 things what are not that familiar to us people. So we will check all these properties one by one, that is operational quality attributes as well as non-operational quality attributes. Moving on to the very first quality attribute of an embedded system. It is response. What do you mean by response? Response is nothing but the measure of quickness of the system. Response is nothing but how fast your system can respond to the input in order to produce the output. You touch a hot surface, you are going to remove your hand very fast. You are going to touch a normal surface, you are not going to remove it probably. So that response time is what you is one of the property what a manufacturer or a designer should look into when he is manufacturing an embedded system. People normally expect the embedded system to be having smaller response time or the response to be as quick as possible. So if the response is quicker, you can say the embedded system is working very fine, isn't it? For example, you are going to meet with an accident, and if your airbag is going to open after half an hour, what is the use? You want it to open immediately, right? That is what is expected by the embedded system. The response of the embedded system should be as fast as possible, and the response time should be as small as possible. Throughput. Throughput is nothing but the number of times your embedded system is going to respond for the input in a given time. For example, if you have a card reader or if you are inserting a card reader, uh, the card reader should be able to read the card, or the throughput of that card reader is measured by how many number of times your card reader is going to read the card in a given amount of time, or maybe in a minute, or maybe in a hour. So that is what it means. For example, if you say that you have a machine which is going to produce some product, how many product that machine is going to produce in a given amount of time, that is called as throughput. That throughput is measured in terms of a benchmark. Normally when the embedded system manufacturer gives you an embedded system, he say that it can produce 10 number of products at a in a given time. That is the ideal one. It may be producing around 8, or it may be producing around 9, which may be considered to be a good throughput of that particular system. So normally when you buy an embedded system, you should check what is the throughput of that particular system, and the throughput of a system is measured by the benchmark. Coming to the third property, that is reliability. How reliable is that particular system? How much can I rely on this particular system? That is what is your reliability. For example, if you are taking a bike from the college, I mean home to college, how reliable is your bike? If your bike is going to get punctured, or if your bike is going to break down every now and then you are not going to take the bike at all, right? You want any of the systems to be as reliable as possible. Normally, the reliability of the system is measured by mean time between the failures and the mean time to repair. Mean time between the failure is the frequency of failures of the system. How many times the system is going to break in a given month, or in a given year. MTTR, mean time to repair, is nothing but how long your system can be out of order when it is undergoing repair. So normally the reliability of the system is given by these two particular terms, that is mean time between the failure and mean time to repair. Moving on to the maintainability. Maintainability deals with the support and the maintenance to the end user or to the client in case of technical issues and the product failures, or on the basis of a routine system checkup. People normally think reliability and maintainability are considered to be they are complementary ones. Yes, they are complementary. If the system is 100% reliable, then the maintenance is zero. If the maintenance is high, reliability is high. So normally maintenance should be as minimum as possible for an embedded system. Maintenance can also be divided into two categories. One is scheduled or periodic maintenance, other one is maintenance to unexpected failures. They are self-explanatory terms. You take a motorbike and after 500 km you take it for a service. There will be no issues with the bike, but you take it for a service. That is your scheduled or periodic maintenance. You take a bike and you go somewhere and it has broken down. You do not look into the kilometer, you directly take it to the maintenance or repair. That is the maintenance to unexpected failures. Very similarly, the embedded system should also be having the scheduled maintenance and also it may be having unexpected maintenance due to the unexpected failures. Uh, some are given here. Some examples are given here. A printer in which the paper jet has to be replaced after every 3000 or 5000 prints. That is your scheduled one. If it is not printing after 2000 prints, then you have to replace the inkjet. Then that is the unscheduled one. So that is what is maintenance. But normally I expect the maintenance to be as less as possible. Availability of the system is nothing but how much duration of time your system is available, and that is measured by this particular parameter. Mean time between the failure divided by sum of mean time between the failure and mean time to repair. I want the availability to be as high as possible. Once I buy the embedded system, I want it to be operational whenever I want it. I don't want it to be undergoing repair, or I don't want it to be undergoing any failure. Security. Security is all about how secure is your data, or how secure your embedded system is in preventing or with respect to the data whatever you have fed. Security will be measured in terms of three terms. One is confidentiality, integrity, and availability. Confidentiality deals with the protection of data and application from unauthorized disclosure. Integrity is with respect to unauthorized modification. Availability is with respect to protection of data and application from unauthorized users. So if all these three parameters high in an embedded system, then you can say that the embedded system is highly secure. If one of the things in this is low, then you can say that the embedded system is not that secure enough. So the fifth property of your embedded system. Final one is safety. Safety is all about how safe is your system when it is operational. So you want your embedded system to be as safe as possible, right? So I want the safety of the system to be high when the embedded system is working. And also the safety analysis should be done. Safety analysis is all about if the system is damaged, how is it going to affect the operator, or how is it going to affect the user who is very close to it. So safety analysis should also be known so that the safety measures can be taken, because you do not know when the system is going to break down or when the system is going to create any damages to the nearby environments. This is with respect to your non-operational, operational attributes of an embedded system. Moving on to the non-operational attributes, the first one is testability and debugability. Let me explain this in very simple terms because you know all these terms in detail. Testability is all about when you are developing a new product, you will be testing. For example, you are developing a program. You After you develop a program, you need to test, you need to check whether it is performing properly. That is done using testability, and there are various testing tools available. Debugability means you have already written a program, and when you are using that particular program for a particular application, it is not responding well. So in that case, you will be debugging that particular program using debugging tools. So normally your embedded system should be testable and debuggable also. So when I speak about testability and debuggability, my testing and debugging will happen with respect to your hardware as well as with respect to software, because my embedded system is made up of hardware as well as your software. So when you're developing, when the things are tested, when the things are done during the development phase, you call it as testability. When the things are done after the product is sold in the market, you call it as debuggability. Moving to the second thing, evolvability. Evolvability is all about you develop a product, and once it is launched to the market, you feel that it has to be the qualities of that product has to be advanced. You develop a product of a bike of 40 which is running at 40 kilometer per hour, then finally you think that it should be running at 60 kilometer per hour. Then you take the same product and you modify it. The modifications what you can do in the embedded system in order to increase the performance of that particular embedded system is called as evolvability, which means that all the embedded system should be evolvable. You should be able to advance it. Next is portability. Portability is all about, let us say that you have an embedded system which has got some hardware components and software components. The software programs are written using C. Now what you want to do is, you feel that system is working very slowly, so you want to replace the code that is written in C using Java. And after you write it in Java, you want to write it in Python. So this particular property of an embedded system which can be replaced as per your requirement is called as portability. Let's say that you have used some hardware components here, and after some time you feel that those hardware components are not operational, or they are not that efficient enough. So what you can do is, you can replace the hardware components with something which will be operating very fast. That is called as portability. Your embedded system should be portable enough in which you can replace both the hardware and software components based on your requirement. That is what is the meaning of your embedded system. Not only hardware and software. For example, let us say that processor. I felt the processor was working slowly and I wanted to replace the processor. So you can replace the processor in the same embedded system with the same hardware and software. So that is what is meant by portability of your embedded system. Moving on to the next one, time to prototype and market. If you look into this term itself, you will know. Time to prototype to marketers, let me say that there was COVID. So I wanted vaccine. So what they did is, they started studying what are the viruses that are responsible for COVID, and they started developing vaccines one by one. So it took a lot of time to develop a vaccine. The very first vaccine what was developed was called as prototype vaccine. After the prototype vaccine was developed, it was tested and it was sent for what you can call clearing by the Indian medical authority. After that, it was sent to the market. Similarly, when you are developing an embedded system, you generally will be thinking, oh, okay, this is the application for which I need to develop the embedded system. Once you know the application, you will start gathering all the components what is required to develop that embedded system. You will combine them together and you will make it work. Once it works for the very first time, that first product is called as prototype. Then you will find that there are some bugs to be debugged and there are some issues what has to be addressed. So you will debug all the bugs and you will sort out all the issues and finally you will let it to the market. That is what is time to prototype and market. Time to prototype and market should be as less as possible. For example, you say that COVID came in December 19 and by around January we had a vaccine. Suppose if you still didn't have a vaccine, then imagine the situation. The things would have gone very bad, right? Very similarly, the time to develop a prototype and the time to bring it to the market should be as small as possible. If you do not bring it to the market, then probably one more competitor will bring the same product to the market and you lose the market. Or maybe let us say that I wanted to develop a mobile phone using Android 9 and it took around 2 years for me to develop an Android 9. By the time I developed this product, Android 11 was already in the market. Do you think the product which was running on Android 9 will be brought by the people? No, they will not buy because Android 11 is already in the market, right? So time to prototype and market should be as less as possible so that your product gets a very good market and it will be sold in the market in a very less amount of time. So this is a very critical factor for your embedded system. It is not about developing an embedded system. It is the time taken for you to develop that embedded system and bring it to the market plays a very important role uh, in the market. Last one is all about per unit and total cost. So per unit and total cost is all about what is the what is the amount you are going to decide that particular unit. Because what happens is the moment you got the idea and to the moment you left it to the market, you were running with no revenue. After that you started gaining profit, right? So even here you would have spent some money. So when you are deciding the per unit cost, you need to think about the revenue what you have spent here in order to develop it. You need to add that amount also when you are selling that product to the market. That is what this per unit and total cost explains to you. Product life cycle, I'll explain it with respect to the video here. With respect to the graph here. See here. This is the initial phase, product development. So by here, your prototype is ready. But when you are developing the product, you had no revenue. Your revenue was zero. When the prototype was developed, you started launching it to the market. Once you started launching it to the market, your product is introduced to the market and it will start to grow. And once it grows in the market, your product will attain maturity. Maturity in the sense, the maximum number of units sold in the market will reach a saturation value. After that saturation value, it has to retire. For example, Nokia mobile phones, when they were introduced initially, it had a very good market and initially it started increasing and finally it reached the saturation somewhere. By the moment it started saturation, Nokia products were not sold further at all. It had to retire and it had to become zero because Xiaomi or Samsung or LG or some other companies brought up their own products in a more competitive price. So whenever you are launching a product to the market, you need to make sure that this time is as small as possible. Faster you develop a prototype and make it reach to the market, more profit you are going to gain in the market, because once your product is launched in the market, there will be some other competitor who is going to manufacture the same product and he is going to launch it to the market, and your product is going to grow and it is going to attain maturity and it is going to retire. So you need to make sure that your product will be launched immediately to the market. So this is regarding the characteristics and attributes of your embedded system. So you have 6 characteristics, 6 plus 5 attributes plus 1 life cycle. So you need to learn all these things very importantly because you might have question on any of these topics for the examination. Thank you.